Today, we're diving into something that is, honestly, a total geological paradox. A mystery that happens hundreds of kilometers right under our feet. We're talking about deep earthquakes, and how on Earth they manage to happen in places where solid rock is supposed to flow, not fracture. So, let's take a trip deep inside the Earth and see what's going on.
Just let that sink in for a second. Everything we learn about earthquakes is about tectonic plates grinding and slipping along these massive cracks in the Earth's crust, right? But what if you could have all the shaking, all the energy, without the crack? I mean, that's a question that just throws out everything we thought we knew about geology.
And that gets us to the heart of this whole problem, what we call the quake paradox. Yeah, it's this fundamental conflict where the rules that work up here on the surface, they just completely fall apart deep inside the planet. And yet, these massive earthquakes are still happening down there anyway.
Okay, so up here on the surface, things are pretty straightforward. Shallow quakes happen in the brittle crust, less than 20 kilometers down. They're caused by slipping faults. We get that. But then you've got these deep quakes. We're talking 300 to 700 kilometers down in the mantle, where the heat and pressure are so immense that rock should flow like thick honey, not snap like a twig. And the cause? For the longest time, it was a total black box.
All right, so to really get our heads around this, we need to take a little journey. We're going to follow a gigantic chunk of the Earth's crust as it gets shoved deep into the planet's gut, into a place where, honestly, the laws of physics start to get really, really weird.
And this right here is our ride, a subducting slab. This is just a massive, cold, dense piece of the ocean floor that's diving down into the hot, soft mantle. Now, this is absolutely key. These impossible quakes, they only happen inside these sinking slabs. This is the scene of the crime, so to speak.
So, we hit 300 kilometers down. The conditions here are just staggering. We're talking pressure that's hundreds of thousands of times what we feel on the surface, and temperatures over 1,000 degrees Celsius. Rock here should be like putty, but nope, we're recording powerful quakes. Let's go deeper. 500 kilometers. The slab is now completely surrounded by this flowing, gooey mantle rock. And yet something inside it is failing so catastrophically that it's releasing the energy of a major surface quake. The mystery just keeps getting bigger. And here we are, 700 kilometers down. This is pretty much the deepest these quakes have ever been recorded. And it is just fundamentally baffling. You've got these powerful, explosive seismic events happening in a place where the whole idea of a rock breaking shouldn't even exist. So how? How is this possible?
All right, it's time for the big reveal. You know, scientists have been banging their heads against this wall for decades, and they've narrowed it down to a few prime suspects, basically 3 different ways a rock could break itself without a classic fault line. Let's meet the lineup.
So here are the 3 big ideas. You've got dehydration and embrittlement, a bit shallower, where water is the bad guy. A little deeper, this transformational faulting, which is a crazy kind of mineral collapse. And way down deep, you've got thermal runaway, where things basically melt themselves in an instant. Let's break them down one by one.
Our first suspect, dehydration embrittlement, is all about water. You can think of it like this. Water that's trapped inside the rock's minerals acts like a tiny, powerful jackhammer, basically prying the rock apart from the inside out.
So, you might be asking, where is this water even coming from? Well, it turns out the minerals in that sinking slab have water literally baked into their crystal structure. And as that slab sinks and gets hotter and hotter, those minerals get cooked and they squeeze out that water under incredible pressure.
Okay, so this superpressurized water, it blasts into the spaces between the mineral grains, basically weakening the whole structure from the inside. This lets the rock fail all of a sudden in a way that looks a lot like a normal brittle crack. But here's the catch. This idea really only works down to about 200 kilometers. Any deeper, and those water-bearing minerals just can't handle the heat. They break down completely. Which brings us to suspect number 2, transformational faulting. And I gotta say, this one is my personal favorite. It's not about rock breaking. It's about rock collapsing. See, the most common mineral down there is called olivine. As it gets pushed deeper, the pressure just gets to be too much. Its atoms literally can't take it anymore, and they're forced to snap into a new, much denser arrangement. This sudden collapse creates a weak spot, which triggers the olivine next to it to collapse, and so on. It's this domino effect, a runaway mineral collapse that unleashes a massive amount of energy. Boom! An earthquake. And for the absolute deepest quakes, we've got suspect number 3, thermal runaway. Imagine you're trying to shear a piece of rock. That motion creates friction, which creates heat.
Now down here, if that heat gets generated faster than it can escape, it starts to soften the rock right along that shear zone. This creates a vicious feedback loop. The softer rock moves easier, which creates more heat, which makes it even softer. It spirals out of control until you get this catastrophic, almost instantaneous failure along a tiny plane. It's less of a crack and more like a super fast, localized melt.
Okay, so we've got our suspects lined up. But how do we prove which one is the culprit? I mean, it's not like geologists can just drill down 500 kilometers and take a look. So instead, they act like detectives, analyzing the seismic waves, the fingerprints these quakes leave behind. And they've found some really, really weird clues.
And those seismic fingerprints give us our biggest clue. See, a normal quake up here on the surface has a really messy, complicated signal. The rupture starts and stops, it rattles around, and it causes aftershocks as the fault settles down. But a deep quake, it's just this incredibly clean, sharp spike. All of its energy gets released in just a few seconds. But the real smoking gun, the thing that tells us something fundamentally different is happening, is what's not there. Aftershocks, almost none.
And this quote really just nails it. Basically, these are one-and-done events. Whether it's a mineral collapse or a thermal runaway, the event itself destroys the conditions that created it. Because it's a collapse and not a crack, there's no fault line left behind. There's nothing to slip on again. No fault, no aftershocks. It's probably the strongest piece of evidence we have that these are a whole different beast.
So, okay, we've got a pretty good handle on how these impossible quakes happen. But, this is way more than just solving some quirky geological puzzle. It turns out these strange quakes are actually one of the best tools we have for seeing what's happening deep inside our own planet.
For one, the exact locations of these quakes let us map the shape of that sinking tectonic plate. We can see how it bends and twists and sometimes even rips apart hundreds of kilometers down. Plus, the waves from these quakes travel through the mantle, acting like a planetary CAT scan. They let us see the mantle structure, its temperature, its composition. It's like a window into the very engine of our planet.
But you know how it is with great science, right? Answering one big question just opens the door to a dozen new ones. We might have our suspects, but the case is far from closed. The mystery of what's happening deep inside the Earth is really just beginning.
I mean, here's a huge question for you. We see these tectonic slabs diving into the mantle all over the globe, but only some of them are lighting up with these deep quakes. The Pacific's ring of fire is super active, but the Atlantic is pretty much silent. Why the difference? We honestly don't have the full picture yet. And then there's this. What if it's not just one of our suspects? What if it's not an either-or situation? It's actually really likely that the reality is way more complicated. You could have a scenario where escaping water kicks things off, which then triggers a mineral collapse, which then spirals into a thermal runaway. It could be this complex, messy cascade involving all three ideas.
And that really leaves us with the biggest question of all, doesn't it? What these impossible quakes really prove is that the fundamental rules of matter, the very nature of rock, can completely change under extreme conditions. And it just makes you wonder, what other secrets, what other completely bizarre physics and chemistry are playing out right now deep in the heart of our own planet?